And then let's go to the last talk in this session, given by Jörg Neumann. Hi, Jörg, are you there?
Yeah, thank you very much. I will share my screen that we can go ahead. And now I think it's fine. So thank you again. Thank you again. My name is Jörg Neumann from the Laser Center Hanover, and I will report on the MOONRISE-payload as proof of principle for mobile selective laser melting of lunar regoliths. And the team consists of the Technical University Berlin and the Laser Center Hanover. As we have heard before, so the main motivation we go for laser melting of regoliths is the additive manufacturing of lunar infrastructure, for example, building shelters or also building launch pads and similar. So, and we have shown already, or also seen in the last talk, that laser sintered object made, for example, from regolith simulant or basalt are possible to do on ground. And the next step we want to go is in space and test there really this technology. It means fusion, laser fusion of regoliths on the moon, and also additive manufacturing on the moon, and technology trade-off we made before identifies laser melting as a favorable technical approach. So therefore, we think laser melting is a good approach because it does not need any consumables like additional binders and so on. And there's also no need of regolith pre-processing, so you can just use it from the ground. Laser melting is also quite mobile. It's independent from direct sun incidents, and you can achieve with a laser a good manufacturing precision. And what's important is a scalable process. You can use stronger lasers, and also automation is possible. And with our instrument idea, MOONRISE, so we want to go for the lunar surface and make there a small-scale proof-of-principle experiment to melt there with a laser regolith pearls, which means 0D objects, lines, which means 1D objects, and also areas, which means 2D objects. And we want to collect their process videos and photos of the fused regoliths on the moon and use this as an input for future process scaling along the roadmap I showed. So we teamed up, as I said, with the Technical University of Berlin. They have a strong expertise in regolith simulant development and their processing. They also have a strong expertise in development of ISRU technologies and system design of robotic systems for construction. And we at LZH have a strong expertise in additive manufacturing. So we do laser powder bed fusion, laser deposition welding, but we also use artificial intelligence for process control of additive manufacturing. We also build laser spaceflight hardware. For example, we built the MoMA laser for the ExoMars mission. We delivered the flight model and the flight spare, and we did all the design in-house and the manufacturing and the qualification of these lasers. The Technical University of Berlin, they developed a regolith simulant system, which means we have Maria-based simulant and Highland simulant, and you can mix them to achieve the local specific mixture to a specific landing site. We are aiming for, of course, you can add olivine, amanites, and other minerals and to chemically adapt the simulant, and also physically adapt the simulant by adding sintered particles and molten glass particles. So we can make the specific mixture according to the landing site. Then the next step was testing the process feasibility of laser melting. We used 9 different simulants, so lithic, chemically adapted, and also the physically adapted simulants with particle sizes up to 2 millimeters, and we processed them in vacuum with a fixed spot that you can achieve this 0D pearls, which are seen on the right. And the fusion starts in our configuration at 35 watts of optical power at a wavelength at 976 nanometer, and you only need less than 10 seconds to melt the regolith simulant. And all the different types of regolith simulant we had could be processed with good reproducibility with the laser. And from this, we deduce the MOONRISE-payload requirements and their optical configuration. So the type of laser source, for example, the laser power, the spot size, beam guiding, working distance to protect the optics against contamination. And with this knowledge, we built a robust engineering model, on the one hand, to show that such a payload is generally feasible, but also to further investigate this MSLM process under more realistic conditions. So here you can see the MOONRISE engineering model. It consists of a system communication, PCB, laser, including the laser driver and the optics. Everything is packed in a hermetic housing to protect it from contamination. And yeah, typically we go for 70 watts of optical output power. We can go up to 140 watts. And as I said before, for the melting, we need about 35 watts. So there should be enough margin. And the power consumption is about twice the optical power, but it's only needed for a few seconds to melt a pearl. The mass budget is 2.7 kilograms for the engineering model, but it could be further reduced for the flight model to below 2 kilograms. And the dimension are 1.5 CubeSat units, and we need a distance to the ground of about 23 centimeter. And we already tested this engineering model for temperature and vibration. But what we need, so we work with a fixed spot, and what we need there is some mobility. So we have to mount on a rover or on a robotic arm to get also 1D or 2D objects. And also for the experiment verification, we need external cameras, which are usually available on a robotic arm or on a rover. Here you can see the testing of the model. So we did the vibration testing. There was a minor issue with the laser driver, but which could be resolved, and also thermal vacuum testing. There was a reversible gradual decrease of optical power above 35 centigrade, but it was still sufficient to fulfill the mission goal. Then we went further to verify the process under different gravity conditions. Here in Hanover, we have the so-called Einstein elevator, which is a driven drop tower. And with this drop tower, you can also simulate lunar gravitation. And we have 4 seconds trial time. We activated the laser for 3 seconds at 105 watts of optical power. We have a little bit shorter time than in the experiments before. Therefore, we had to go higher with the power, and 1 second to cool down the melt. And the laser melting process was in vacuum again, and we had also a high-speed camera to observe the process. We had to slightly compress the regolith a little bit in order because of the low gravity conditions. So here you can see the process here under 1G with uncompressed regolith. So you see on picture 1 the sample container, on picture 2 the melting starts, some particles are ejected, and on picture 3 there is a sphere of molten simulant, and on picture 4 it's cooling down, and on picture 5 it's removed. And on the lower right you can see the different gravity conditions. So these are the trajectories of the ejected particles, and you can see for 1G there is a different trajectory compared to lunar gravitation, for example. So here you can see a comparison between the different results under different gravity conditions. So 1G lunar gravitation and microgravitation. We did 15 drop experiments each, and the volume and mass is nearly identical for all gravity levels. You have a smooth surface with some melted particles on the bottom. And if you do a microsection or a micro CT, you can see there are bubbles inside. You have about 50% porosity. And if you look at the 0G samples in the micro CT, so the bubble distribution seems to be a little bit more even, but the take-home message is that the process works at 1G and lunar gravitation and even at 0 gravitation. So the next step there was also to make larger objects. Therefore, we accommodated our engineering model on a robotic arm. We had a motion speed of 1 millimeter per second at 120 watts of optical power, and we go line by line. In between, we had to switch off the laser to limit the deposited heat and avoid cracking, but we achieved 20 by 20 by 4 millimeter sized solid objects. So in summary, I showed you a proof of concept payload for laser-based fusion as part of the roadmap for 3D printing of regolith structures on the moon. We did a feasibility study and also built an environmentally tested engineering model. We verified the fusion process on ground, so in vacuum under lunar gravity, and made 0D, 1D, and 2D objects. And in future work, so we recently received a new funding period to build an FM and also some money for accommodation on a commercial lander. And of course, we want to extend our ground test campaign and also include artificial intelligence for remote result evaluation. And yeah, finally, we want to verify the MSLM process on the moon. Furthermore, we work on implementation of 2D beam deflection, laser power scaling, parallelization, and so on for potential follow-on payloads. And this work was funded by the Volkswagen Stiftung, by DLR, and also by ESA. So thank you very much for your attention.
Very interesting, Jörg. Thank you very much. Are there any questions? Yes, there's a question from Philip Price. Exciting results, thank you. Do you think you can also make 1D, 2D objects in the Einstein Tower? Is this available time sufficiently long?
Yeah, there's a problem is we have only 4 seconds for one drop, and we need very high laser power to do so. So we have projects to also test the limits of the Einstein elevator. You can go for stronger lasers, then you have a faster speed. That's something which is currently under evaluation.
Okay. Yeah, there are no other questions, and I might have a quick one. You mentioned that you are now transitioning from EM to FM. Just for curiosity, what are the major development steps? Is your EM already sufficiently representative, or in terms of hardware, for example, what would be the major transition from EM to FM for this hardware?
Yeah, so of course the housing is very stable, so this would be there we can save a lot of mass, and now we use many commercial off-the-shelf electronics which would be replaced. So we tested already this commercial off-the-shelf electronics separately in thermal vacuum chambers for vibration, and there are some minor points which could be improved.
Yeah, you mentioned that you need to have a certain operational temperature, and you also mentioned that you would like to be accommodated on a robotic arm. What about the thermal concept?
Yes, that's also something which is currently under discussion. It depends also on power available, but just for a bead, you only need a few seconds to melt this, and there is not much heat generated during that time.
But you need to keep the hardware itself warm.
Yeah, of course. Then we will work with MLI and so on. So this is, of course, still missing, but we need to have the final description. Yeah, but there's enough work to do.
Thank you very much. Yep. Very interesting. Okay, so if there's no more questions, I don't see any, then I think this concludes our morning session.